Right, so welcome to another edition of the CLSP seminar. It's a pleasure to welcome today's speaker, Professor Hanseok. Some of you have already seen him in our building for several months now, so you might be wondering why I'm welcoming him now. Well, it's just a welcome to the seminar. He's a visiting professor in the Electrical and Computer Engineering department, and so you'll get a chance to see him if you have questions and all, not just after the talk today, but until August of next year. Professor Ko started his education at, well, I guess, once we skip high school, at Carnegie Mellon University, where he got a bachelor's in '82 in electrical engineering. Then he moved to this area. He got a master's from University of Maryland in systems engineering in '86, a second master's in electrical engineering from Hopkins, and then finally a PhD from Catholic University in Washington, D.C. in '92. He has worked for extended periods of time in this area. So he was at the Naval Surface Warfare Center, where he worked on radar signal processing and infrared image processing. His interests include signal processing, and in fact, let me read a few to you. Signal processing, data fusion, navigation, tracking, visualization. And he's going to talk to us today about this interesting problem of multimodal interaction. So you have a talking face that's talking to you. Let's say your email is being read to you, and if it's from your mom's face pops up on the screen, and she scolds you and says, "Why haven't you eaten lunch on time?" So you want to make the lips move in sync with the speech. How do you segment the speech signal to do this? And this is an integral part of a bigger problem of building natural man-machine interfaces.
Okay. Well, thank you very much, Sanjeev, for a great introduction. It's a privilege for me to be able to have this opportunity and then actually be able to speak in front of you, student body and faculties of a great prestigious university, right? Korea University is actually one of those comparable colleges in Korea. So what I want to do actually is to, before I get into the technical aspect of this talk, do a little bit unconventional, unorthodox way, and give you a little bit of glimpse of Korea with respect to. I'm going to still, try to maintain the main theme into speech. So I'd like to actually give you a little bit of background on the how Korea is doing in terms of speech recognition and its technology, so that later on, sometime either later this year or next year, there are programs from NSF that actually supports graduate students to be, doing some research activities in Korea. So this is one of those, I guess, reason why I want to give you a little glimpse of that. And then I want to get into the main topic, which I guess Sanjay probably gave you a great synopsis of the talk. So I'm going to basically talk about the Lip-Synch, the concept of Lip-Synch, and some of the involved algorithms, which is probably taking in stages. So there are 3 stages of algorithms that needs to be taken for the Lip-Synch application to work. And then, of course, it is still an infant stage, so it needs a lot of work. And so even though I'm going to try to show you a little demo, that probably is meant to give you that there are still some future work. Okay? You probably have seen enough of maps by now, right? Well, this is Korea. I mean, geographically, it might be like very far away from here. See, there is actually a flight from Dulles Airport to Seoul non-stop. Takes about 14 hours. But other than that, it's all right. Korea University is located here in Seoul, which is the capital city. This is the city map, and right in the middle of downtown is where Korea University is located. The reason I say that Korea University is comparable is because it resembles very much like Johns Hopkins. Okay?
It looks more attractive than
The structure-wise, the building-wise, in fact, the founder, what they did was that they toured around the country here in the States. They actually picked some of the model buildings, and built this thing, 1905, approximately about 100 years ago. They modeled after Harvard, and I haven't heard, but I think it might be Johns Hopkins. Okay? It is actually the largest private university in Korea. It boasts about 25,000 students and 1,500 faculties. The student body constitutes top-ranking students from high school, top 1 percentile in the so-called SAT equivalent in the US. And some of the prestige could be reflected by the sheer number of cabinet members, the secretaries, the ministers. 30% of the cabinet members are, on the average, came from Korea University. Okay, the specific department that I belong to, it is called Electrical and Computer Engineering, is established not very long ago, 30 years. So 30 years young. This is some of the buildings, what they might look like, and this is where the EC department is housed. So there are a lot of resemblance here at Johns Hopkins, and you won't feel anything like being foreign, okay? I have this lab as a director. It is quite, I think, from the American standards, not very small. It's sizable. I have about 7 PhD program students and 15 master's degree program students. I put zeros here for reason. This is where you guys can go in. All right? All right, so I'd like to increase the number something greater than 0 sometime in the near future. The research focus, as Sanjeev had mentioned a little bit, my main research focus is, of course, speech. Some of my background, it turns out that I did have a lot of Defense Department experience, and some of my research focus happens to be in acoustics. So good transition from the defense to non-defense work happens to be speech. So about 6.5 years ago, that's where I kind of put together the lab focusing on speech. And Lip-Synch is one of the element, we should say, in speech area that I'm focused on. If there's more information that you'd like to have, you can always visit the website. Okay, the speech industry in Korea, just a brief highlight. It's not very long, okay, as you might have expected. It began about 15 years ago by KAIST is an academic institution in Korea, more like sort of like a technology or technically oriented school. We have a very large research oriented institute called ETRI and Korea Telecom, which is sort of like an IBM type of institution. So these are the organizations that kind of have their thrust on speech-related research effort. Nowadays, the entire nation is giving a lot of heavy considerations and effort to push the speech-related industries. So two government branches, the Ministry of Information and Communications, as well as the Ministry of Commerce, are taking leading roles in the supporting R&D and other commercialization type of efforts. The major academics in speech nowadays are KAIST, Korea University, Postec, and SNU. Some local Korean companies that I don't know you might have heard is Voiceware, Voice Media Tech, Xtel, DNM. So some of these companies were established in the last 2 and 3 years ago. So it's relatively new, but they are coming up and coming very strong. Some of the non-Korean companies are now taking their base there. Speechworks, IBM Korea, LNH, Nuance. They were established their base in Seoul. Let's see, early this year or late last year. And the reason is because somehow they believe that because of the fact that Koreans nowadays have the visibility as the highest internet users in the world. So therefore, a lot of these companies think that a lot of business could be introduced out of that.
What is that number, David?
I'm sorry?
What is the number? What fraction of Koreans are online?
Well, I think, I guess it really depends on the number of housings. The population there is about 45 million, okay? I think about 1/3 of the population are frequent users of internet. So that really includes like kids like little elementary school up until, you know, people in their 50 years old in that age group. And also the availability of internet and communication infrastructure. And I mentioned about the housing, just about every homes, they have access to internet. So the internet type of infrastructure is visibly available there. And as I mentioned before, some of these companies do believe, in fact, that it is one of those countries that could actually generate business out of making products from the speech-related technologies. Okay, now I'm going to get into the main topic. The Lip-Sync. As briefly Sanjit had mentioned, okay, the concept of Lip-Sync is to activate the avatar's lip motion in sync with the speech signal in real time. Okay, some of the applications could be like this. It could help out on computer graphic animation in noise environment. Okay, lips movement could help you know, better listening, and the avatar's computer chatting could be is one of the topics that a lot of business could be produced out of that. Foreign language pronunciation study, as well as you know, speech pathology, could be also exploiting the lip-sync type of technologies. So it is very useful, and not very much of an effort has been done, surprisingly. Here at the NC State, for example, it tries to extract the lip parameters. Lip parameters meaning like the lips, you know, the length, how high it should be in terms of, you know, modeling the lip motion itself. There's a company called Lip-Synch, which is to try to perform the lip syncing, okay, but not in real time. So this is sort of like an offline type of lip sync application. Japan did some work on syllable unit based speech recognition or lip sync, and I think I guess based on my survey, we are the first ones that are actually doing something in terms of the voice speech, extracting the voice speech and invoking some kind of recognition that activates visons. Okay. So the overall objective of the research is this: we want to activate lip motion in sync, okay, with the presence of the speech utterance, and it has to be done real time. It is not an easy task because of some of these challenges. The phones are known to be very short. Okay, so we're looking at very short acoustics signal. And out of that, we need to extract enough of information to actually generate the visons for the motion to take place. And there's a lot of heavy processings involved in this, particularly because the avatar itself also, if it is done using the same processor, it takes up a lot of processing load. HMM-based speech recognition also is a little bit more heavier than the other recognition technologies that I'm going to address soon. And the other thing is that it has to be in real time. That's the most probably significant thing, that it has to be done in real time. And we want the activation and the lip motion to be more naturally done. So these are the kind of challenges that we are facing with. And this is the block diagram that shows how the stages or the procedure is actually taking place. We could break it down, the entire process, into about 3 stages. One is to first detect the regions of voiced segment from that of the unvoiced segment as the first stage. After the fact that it generates voice or voiced part is detected, then we want to perform segmentation. Okay? And then after segmentation, we want to draw enough feature extraction so that we can perform some kind of a recognition. So all of these procedure looks very much like the speech recognition type of processings that take place. But here, once again, the challenge is that it has to be done real time, and we really don't have the time to kind of make any predictions, okay, based on the statistics. So given the frame, given each of the frames that are coming in, we need to make decisions right away. On the left-hand side, it's sort of like showing, what's taking place on the right-hand side. So each of the, as the speech utterance is coming in, we segment. I guess segment in terms of frames, and each frame we want to make sure that either that frame contains enough of information that can tell us that it is the voiced part versus unvoiced part. And then after that, we want to invoke some kind of a segmentation rule that segments from one phone to another. And within each of the phone, we want to perform some kind of a feature extraction and then perform phone recognition so that each of the phone that was recognized could be used as the activation signals that drives the avatar.
What I'm trying to understand is what is the ideal information you need to do lip-sync? So suppose I could do any speech processing perfectly. Mm-hmm. Is it enough to get the identity of the phone, or do you need even more information than the identity of the phone? Because once you know what phone it is, I suppose it follows
right.
most of the time whether or not
if the phone is identified, that should be enough.
That should be.
Right. And there are about 13, 14 bisems that are representative of the facial, the lip models. So basically, this is what the thrust is basically have some kind of means to identify what each of the phones are so that they can be mapped into 14 different bisems, which is enough to drive the motions of the lips naturally.
You have some kind of interpolation between the bisems?
I'm sorry?
Graphically, you have some kind of interpolation between the bisems,
right?
And that's done as the last step of processing.
Right. Mm-hmm.
Okay.
Yeah, which I'm going to talk more about the avatar later.
That's fine. I do have one question about this diagram. I'm not seeing a language model here. You don't use any. You just extract everything directly.
Yes.
From
right.
the speech stream.
Yes. Mm-hmm.
I'm curious how the phoneme accuracy compares with hidden Markov model or other methods that use language model.
Well, hidden Markov model is I mean, as long as it is offline, it's definitely better.
But how much better?
I really don't have any numbers in terms for measures, but we use HMM just for verification. Mm-hmm. So that's sort of like our benchmark is HMM.
Right.
Follow-up question to my previous one. So obviously you don't, like if you had the phone identity, that would be sufficient to do the lip sync. But from what you're telling me, it's not necessary because you have only 13 or 14 bisems.
Oh, I see. Yeah, right.
Correct.
Okay, so there are like say 50-some phones. Okay.
Right.
We don't really. So I'm going to be talking about those kinds of things later. But essentially, we don't need to actually identify all phones. Okay, we could map certain phones together. Basically, it's essentially vowels versus or voice versus unvoiced speech parts. So out of the voice ones, we want to perhaps maybe segment different vowels. So segmentation is actually meant for once it is detected, once the voice part is detected, is it certain vowel versus another vowel? And it is the vowels actually that's the driver, the main driver of your lip motion. Okay, I guess I probably mentioned that already here. So as far as the main driver of the visor happens to be the voice part, and out of the voice parts, particularly of the vowels and voice consonants, okay? So the first stage is actually to be able to then tell whether or not the particular speech segment is voiced or unvoiced part. So we need some kind of a detection scheme to make that kind of identifications. Now, how do we know if a certain segment of the speech is voiced? The kind of event or evidence is the fact that we look for periodicity is one of the good evidence. For the unvoiced signal, it resembles very much like noise signal, so we don't expect to have any kind of periodicity there. For voice signal, as you know, that it is based on the GCIs, glottal closure instance, which is the generator for the periodic signals. So that's what we basically look for. If the speech pattern itself contains some kind of a periodicity. And pitch period, therefore, is the kind of thing that we look for, we search for. And there are a number of voice signal detection algorithms, which is mainly to search for the presence of GCIs or periodicity. The first one is called dyadic wavelet transform method. And then we have bandpass filtering method. And then we have a combination of actually these two things called variant threshold method. And let me talk about these three methods focused on detecting the voice versus unvoiced speech part. First thing is the dyadic wavelet transform. This thing is meant for speech patterns in time domain. So this is a time domain operation. It's essentially, you could consider this as sort of like running different low-pass filter, okay? By varying the scales of the wavelet transform. If you increase the scaling to different scales, you will see, for example, here's one waveform of the same thing, which is extracting out of this particular segment of your original speech. Which is expanded, and it looks like this, okay? Now, you invoke your wavelet transform over that for one particular scale, and this happens to be at scale 3. And then you have another one, scale at 4. So compared to this one versus this, you'll notice that as you increase the scale, it looks more like you're invoking some kind of a low-pass filter, okay? So a lot of these, the wiggly type of waveforms, it becomes a little bit more smoother here on the lower graph. Now, what we look for is that at each of the maximas, okay, for different or adjacent scales, we invoke some kind of a little window and look for the location of the maxima. They may not necessarily match at exact same location, but then we can introduce a little bit of threshold. So once it belongs to within that tolerance, then you can call it as the local maxima there. And each of the maximas is where we want to label and then look for and reason out to see if that each of these maximas, in fact, has some kind of periodicity by looking at the distance, the GCI distance. So that's the wavelet transform method. And the second method is called bandpass filtering method. And this is done over, as you know, bandpass filter itself says, done on in terms of frequency domain. Particularly, this is because the bandwidth of the voice signal is predominantly located within between 30 to 500 hertz. So what we want to do is that we want to invoke the bandpass filter over the speech signal, and then search out for the once again the maximas and where they occur. So from the original speech signal, this is the filter signal, and if we zoom in this particular location, this is what that looks like. And if you invoke the bandpass filtering, this is what the result. So out of the bandpass filtered signal, you look for, again, each of the local maxima. And then search out if they, in fact, constitute periodicity or the locations of the GCIs. The third method is the variant threshold method. As you can see, each of the method, for example, the bandpass method, you'll see that the maximas could be located at different intensities. That might introduce incorrect decisions. So what we do is that we kind of divide the regions into a number of different threshold levels, and then search out or reason out for the periodicity to occur, so that you can kind of confirm or verify if your GCI is in fact periodic. Here's an example. You could see or verify the periodicity by performing this kind of averaging out. For example, let's say you have a number of these local minima based on some kind of filtering. Then what you do is that you compute the average, and then at each of the threshold where the maxima occurs, you want to compare that, the location of each of the pKs, against the mean value. And if there is some small tolerance, which is less than, say, epsilon, right here, then we can confirm that that is the voice region. And if it is not, then what you do is that you kind of bring your threshold level up to the next level, and therefore look for another periodicity there. So you do have layers of these thresholds, and use that kind of reasoning to look for, search out your periodicity that occurs in your speech signal. Here's a result of the comparisons of all these three types of algorithms. Let's say given a speech signal, this is your original speech pattern, and then invoking your dyadic wavelet transform. Ones with these bars represents the locations of GCIs. As you can see that you do have a lot of work. From here to here is the voice region, so if you kind of line up here and here, you should have all these bars occupying the entire region, and you notice that there are some empty spaces, which means that it's missing GCIs. Therefore, it's not really doing a great job there. Whereas here in the bandpass filter technique, you notice that there are some of the regions here that are being overly done. So even though the bandpass method finds the incorrect, however, GCIs, it is still okay. Well, it should have said correct GCIs, but it is not the pitch period. It is not the correct pitch period. So it does find the regions of GCIs, but it cannot produce the correct pitch period. Is the problem with bandpass. With the variant threshold method, you do have because it is sort of like what should I say? Somewhere in the middle between wavelet transform versus the bandpass, it does produce the correct regions where GCI should be occurring. So variant threshold is the method that we take for the implementation of the Lip-Sync algorithms. We then move on to the segmentation. So once we have detected the voiced region, which basically constitutes the vowels, we want to then segment one vowel versus another vowel. A lot of the vowels look about the same. For example, I've shown here with the same lip motion of three particular type of vowel phones, ah, ya, and wa. Okay, they all, if you kind of move your lips or produce the sound, you'll notice that your lips motion resembles each other closely. And so we could, in fact, kind of merge the similar ones together. And then we have about 1, 2, 3, 4, 5, 6, 7, about 7 different categories of vowels that we need to segment. So the segmentation algorithm, by the way, even if we make these kinds of mergings, we want to essentially search for some significant event that changes in a frame, some kind of intensity changes, which is significant enough that we can call that there is some kinds of changes in the segment that takes place. So in a waveform, what we do is look for the changes and where that occurs. What we do is we essentially model the acoustic signal into autoregressive statistical model like this, and then use that information to generate the generalized likelihood ratio. Here's one aspect where we could kind of formalize the segmentation a little bit. Now, out of the model, we then parameterize the model into a vector form like this, which is to map all these coefficients as well as the driver into a vector form like this. And then the likelihood ratio, the generalized likelihood ratio is sort of like reflected in this picture, where what we do is to essentially come up with two possible hypotheses. One is that there is no change, like this, and one that there is some change. Okay, so the GLR method is a ratio of the likelihood of this thing over this particular type of event. So the null hypothesis is where there is no significant change, and the alternate hypothesis is a case like this where R is such that that there is some significant event where the region on the left-hand side of R and the right-hand side of R is significant enough that that the ratio actually is greater than some threshold. For example, a change is detected, okay, if the likelihood ratio of the two hypotheses as function of these parameters is greater than some threshold. So essentially, the idea is to reduce or simplify this likelihood ratio, and then come up with, and as you kind of slide R from left to the right, which is to search out the location of R where d sub n becomes maximum. And I think there's another picture that kind of shows you better. If you kind of carry out the likelihood ratio, it simplifies to this particular very simple form, which is in a form of functions of the variance, and you know, intuitively that's sort of like makes sense, because if there is no change, you should see you know, a constant variance here. Whereas if you do have some kind of changes here, say at R, the variance at this point should be different than the variance at this region. And that's what essentially this thing is all about. So, so the idea is look for R where that significant change, d sub n R, as you slide R from the left to the right, where that occurs, and if the occurrence of the value of the ratio is greater than some threshold, like here, some threshold, then R is your segmentation point. In order for you, by the way, to make the decision where the threshold ought to be, I guess it really need to take a number of experiments to kind of pinpoint the proper size of your threshold. The second type of segmentation scheme is done over in frequency domain. It is called Lukowicz implication method. This is the spectrogram for the spectral changes. Before, for the GLR method, what we did was to look for the significant changes in time domain, whereas here in this scheme, you look for significant changes in spectral domain. For example, this is one particular segment in spectral domain that looks about stationary. In other words, no significant change has occurred. Whereas here, just for the purpose of clarification, notice that this region is a little bit more intense than the region on the right-hand side. So we could consider intuitively, visually, that there is some significant change on the left-hand side. So we are looking for that kind of locations where significant change has occurred. And Lukowicz is a method that shows, that measures up the similarity of the changes of your data, spectral data. The concept is like this. Lukowicz is sort of like a mapping of your similarity measure into a value between 0 to 1. Notice that if you have your data that are close enough together, we can consider that they are similar, like this. If they are kind of far away each other, then we can say that they are not similar. Lukowicz implication kind of is a mapping tool that maps the similarity between 0 to 1. And as you can see that the similarity, for example, as defined by Lukowicz operator, is that A is similar to B, okay, by using this equation. And this equation essentially is going to compute, is going to approach to 1 if A is close enough to B. And if it is very much different, then the value is brought down to 0. So it is that kind of scheme that the concept that the segmentation is performed. Here's the approach for the actual speech pattern. What we do is that out of speech, we map them into about 18 different critical bands on spectral domain. And then for each of the spectral bands, what we do is that for different frames, the adjacent frames, we compute the spectral distance. And for each of the patterns to its adjacent pattern, we compute the average of all similarities in one frame. And then based on that, if it is close to 1, we can consider that they are similar. If it is to be approaching 0, then we can say that they are not very similar. The decision rule, by the way, certain decision rule has to be applied over the result, because there are also certain cases. For example, we want to make sure that the possible occurrence of a phone cannot occur in the same frame. Okay, in other words, you don't want to, for example, segment two phones, or the possibility of occurrence of two phones in one particular frame, which is about 32 milliseconds. So you want to eliminate one of the two occurrence of the significant changes. And you could do so by going through a number of these decision rules. And then, as you can see on the left-hand side, some of these things we invoke a certain threshold at the beginning. And then, so these are all possible members of places where you could have segmentation. However, like here on the left-hand side in this corner, if they are kind of clustered together, only one of the group can be the candidate for the significant changes. The ones that below the threshold is the one that tells you the similarity is very small, which means that the difference between the two frames are significant. So after going through the decision rules, for example, including eliminating the local minimums in 32 milliseconds, you could judicially eliminate those locations where it could have very little chance of being the changes. As a result, here's one waveform that was done by the Lip-Synch algorithm versus one that was done by human. As you can see, this is where a good segmentation has taken place using the Lip-Synch algorithm. Here's where the overlap between the Lip-Synch point versus the human, the person that's actually labeling it has taken its point there too. And as you can see on the entire plot, you see a lot of the resemblance. So Lip-Synch, in fact, is very good, shows a very promising result as far as being able to segment the vowels that are adjacent each other. The next stage, out of the 3 stages, okay, we talked about the detection, then we talked about the segmentation. The last one is the recognition. So within each of the phones that was segmented, then you want to perform some kind of a recognition scheme. There are various phone recognition algorithms, and as it was mentioned before, the HMM-based recognizer could be used. It does produce a lot of good results in terms of word recognition. Only thing is that it takes a lot of time. I mean, it's unfit for real-time application. So we have to kind of look for other or alternate approach. This is the nearest neighbor rule test, where some kind of a matching pattern matching algorithm could be applied. It is a little bit simpler and definitely a lot faster than HMM-based recognizer. So that's what we kind of our direction has gone to. So look for evidences, and they could be done in terms of different features. So the kind of features that we have employed were like the ratios, the formants, and you know, some of the features that we use for HMM, like MFCC, delta MFCC, and log energy. So the features that are used, particularly for HMM type of recognition, are also still employed, but not in the same sense as HMM, but as features that are used for nearest neighbor rule test. We also perform warping of the signal into bark scale, so for better separation. I'm going to show you why. And as I mentioned, that there are other features that are used well a lot in the HMM type of application. Here's a reason why bark scaling is used. On the left-hand side, you see a lot of the overlaps because they are kind of close to each other. On the bark scale, it kind of separates all these possible vowels. So it is one step that we kind of inserted in between to make it better separation. So based on all these features, we cluster these features into number of models, where each of the models represent certain phones or vowels. As I mentioned, on HMM, comment is that since one phoneme is too short, which is about 50 milliseconds to about 200 milliseconds, and each phone should only take maybe 1 or 2 possibly frames, and we have to make the decision based on 1 or 2 frames. And it is very short for HMM to make any type of robust phone recognition. So for Lip-Synch application, because we do require real-time results, and overall, the recognition result is not very good because once again we are still fighting for real-time classification or pattern recognition, and that's not very easy. So there are certainly more research that needs to be done here in the recognition, and we are looking into not only HMM but also GMM, which is somewhat better as far as taking time is concerned. At the same time, the accuracy is not as good as you might have expected. So there needs to be some other type of approaches to improve on the recognition performance. So right now we're just using very ordinary pattern recognition, nearest neighbor rule type of approach. The Lip-Sync system that we have implemented together is supposedly meant for real time and should be able to handle continuous lip-sync. And for recognition, we applied nearest neighbor. And for segmentation, we use both GLR and Leukospix implication method. The facial model is not the work of ISPL. It is actually borrowed from another lab at Korea University. And this is that block diagram. So out of the speech signal that was presented, the input device will take it and perform, once again, the 3 things: detection, the segmentation, as well as recognition. So detection and segmentation is done here in this block. Out of that, we extract out the feature enough for the recognition to take its place, to take its course. We essentially break down into 7 vowels, or merge into 7 forms of vowels, and they're sent into the activating the avatar unit. So these are the 8 events, including another one here, which is suppose NON, which is sort of like etc. Besides the 7 vowels, anything other than that, other than the 7, we classified into none. So they are the Visum events that activates the avatar. A brief overview of the avatar modeling is that each of the face model is done with the muscle modeling as well as the parameter modeling. For the parameters, for example, we use the lips width, the height of the lip, and things like that. Okay, the muscles in that are shown here in red lines indicate the ones that are used for the particular avatar that we're going to be seeing soon. So the composition of the facial model is done by, first of all, the model data is read, and then some kind of textual mapping is done. Textual is rendered, and then we can define the muscle and lip parameters which was mentioned just a slide ago, and then the facial model is generated. So based on these flow here, this is how each of the face is constructed. So each of these lips that's going to be activated is essentially done by identifying the Visums that activates the muscles and lip parameter models. Here's an example of the signal that we're activating the avatar model. Here's the picture of vowel A, E, O, U, and A. Okay, so we have 1, 2, 3, 4, 5, 6, about 7 different models that we activate. Before I show you a little demo on that, let me make a couple of conclusions and kind of I tell you where we are in terms of working out the research issues. For this particular presentation, the variant threshold method for pitch detection reasonably works okay. Leukoic segmentation in spectral domain is actually better than the GLR. For now, NNR is the approach, and we're looking diversifying the approaches as far as recognition scheme is concerned. Because I'd be very much looking out for your suggestions as well for any improvement. Many issues that needs to be still worked on. We want the segmentation to be more reliable, and we would like to, if possible, replace the current NNR test scheme with a more reliable recognizer. We're looking into a number of GMM type of solutions with some modifying schemes in between. But it's not really so far giving you good signs, but we're still looking into avenues. Also, we like to increase the recognized phonemes for we should like to also include the voice consonants as well. There's also a lot of, because of the fact that it takes a lot of computational load, we want to optimize, including the program code itself, so that processing time can be done using one single processor. Right now, it cannot be done. In other words, you need to have like 2 processors, one for the avatar, the actual image itself, and another processor for the speech part. So for you to be able to actually see the lip motion being activated by speech in real time, I need to have 2 separate processors to show, which I don't have that here. Also, the natural lip movement is something that we desire. So lip movements has to be done more naturally, and like to also have better facial model for natural looks. Okay, this is what I have for the presentation, and let me also show you a little bit of model that at work. This is the model, the facial model of a female here on the right-hand side. What I have here is a recorded version. As I mentioned, because you need to have 2 separate processors, okay? Because of the heavily, the computational load is rather too heavy. So here's one particular example.
A, E, I, O, U, O.
Okay, so here are the results of the vowels that were detected.
안녕하세요. 만나서 반갑습니다.
Okay, I guess it could have been better if some kind of an English utterance could be made, but essentially I'm hoping that you could see the lips being in sync with the utterance, okay? Essentially it's Korean that sentence that says, hello, my name is so-and-so. Here's another one, another example.
오늘도 좋은 하루 되시기 바랍니다.
Okay, so this is another example. So as you can see, the facial model itself is not completely natural, okay? And we like to have a better, model, the facial model, and also, we like to have the ability to be able to actually show the whole thing in one screen, the two things going together at the same time. So that's something that we're shooting for. Just for the entertainment, I'm going to just type in a sentence here. Which is which has a lot of vowels here. I'm going to just utter it out for you. Okay, it says 나는 바보야. Okay, so you have like Maybe I should be teaching you some Korean here, but a little short lesson in Korean. But anyway, the first one says has contains The second character contains and o, ya. Okay, so you have a number of these vowels. 바보야. Can you kind of get it? 나는 바보야. Okay. Anyway.
Can you do it again?
All right. 나는 바보야. All right.
So when you were playing the sound clip, it looked like her face was a little choppy, just in terms of the transition. But when you typed in the sentence,
This is really, there's no speech recognition in there. It's just a driver.
so but what's,
Text to motion, I guess. Text to motion.
so why was it choppy when you were playing?
Because the motion model itself is choppy. And I mentioned that still needs a lot of improvement. Right. I don't know, maybe somebody else here here on campus might have better models, which I haven't seen it. And I'd be interested in exploring that.
There is a group in the Center for Imaging Science.
Oh, okay, somebody else is doing that?
No, they don't do quite this, but they have some techniques for sort of rendering faces.
Oh, okay, yeah. Well, a lot of people are doing that, so this is not like very unique, okay? I mean, there's just a lot of people.
But the coupling with real-time speech is, I think,
Right.
something that many people are doing.
Right, right, exactly. That's why I'm still maintaining, to include that as one of my research focus.
Could you see sentence one again, please?
I'm sorry?
The sentence one, can we watch again?
안녕하세요. 만나서 반갑습니다.
I don't know. It didn't quite, well match. Yeah, it's like I said, there's a lot of mismatch, and once again, the recognizer is only focused to the vowels. Okay, so we'll still have to go through, identifying or recognizing the voice consonants, and it's not perfect. So the idea is to be able to segment and identify more visems than just 7. Okay, prefer say over 14, which is the number of visems that require that are standard in these days. for standard the face motions.
Is there a reason why you are focusing only on the voice segments? Is it because the unvoiced segments are very difficult to?
No, because the motions, the lip motions, are primarily are activating based on the vowels, the voice parts.
Right, but
by and large.
If you say pa or sa or ka, all of that is unvoiced. I mean the consonant part, but it's a very different.
Little bit of right.
Or
Yes. I guess those are the ones that we're missing. Right. Yes. So right now we focus more on the vowels first, then we move on to including those kinds of things. And yeah, I mean this is not an easy task, especially because I only have like one student working on this thing.
In the examples that you played, the two sentences, so essentially there is a speech input and offline you have done the recognition and then you're synthesizing the face.
Right, yeah, it's kind of...
How accurate is the recognition in these two cases? Is because I don't know the language, so I don't know.
Yeah. Once again, we really haven't done it in terms of the numerical measures. We only kind of visually, seeing and kind of making it notice. And I would say it's doing, relatively all right, but needs more improvement.
Yeah, so in this example, in this sentence, is there an error or is that?
Oh, it's right now there's no error.
Okay, the ones
Yeah.
you're showing us there are no error.
Well, yeah, very little error.
Okay.
Yes.
Because I'm trying to think of how it
You mean like this one or this one?
the sentence.
Yeah, the sentence, yeah.
There is no error.
Very little error, if there are any errors.
Okay,
Yes.
because the question that I had is, what happens to the lip-sync? In other words, how does it sound to a native speaker of the language? Or basically someone who understands the language.
Yes.
Will it confuse me more?
Can that person recognize the words by looking at just at the lips?
No, more importantly, suppose there are recognition errors.
Right.
What happens to the visual perception? Because after all, the
Oh, I see.
motion
I
is
see.
done based on erroneous.
I guess we can ask one of the Korean students here. It's helping. In other words, visually, seeing and because the sound is matching, to me, I mean, it helps. It's more. I mean, it clarifies the sound by looking at the lip motion because they are in sync. Based on a native Korean speaker.
So what I'm worried about is that
If there's a mistake.
the recognition error, then it is reinforced by the fact that the visual.
Yeah,
also
definitely,
matches
yes.
the error.
It will definitely, right, exactly, yes. The visually, because it's going to activate wrong, lip model, yeah, you should definitely show wrong lip motion. If it is actually detected and then recognized, incorrect phones. Right, there's no automatic correction schemes here. And like I said, the only reason we have done it like this is because we couldn't get another processor that could, support the images.
I just want to clarify something. As you're going through, it seems like you're recognizing the phones, but then you have to translate them to these bises.
No, phones are basically, if they are recognized, yeah, they are.
Yeah, but as you mentioned, there's only
Yeah,
15,
right, yes,
so
yes.
So would it
Merge
make
it.
more sense to try and find the acoustic correlates of the bises, and therefore you only have 15 of your neighbors to pull out, where instead of having to recognize just a single number of phones, and then collapse after the fact anyway? Or is that not what you're doing? And I don't know whether or not they're similar enough that it would make any sense anyway.
Yeah. Anyway, either way, 5 is easier than 14. Okay. So yeah, I mean, I guess you could have done that way too. I mean, that approach. But still, if we're looking at like 14 different things to search for, we thought that would create even more challenges. So yeah, but I guess you could do it that way. But
I mean, there's plenty of reasons why you want to recognize phones that speech anyway, but if there are only 15
Yeah, primarily is what I heard. It's about 15. Predominantly 14, 15 bizems would be enough or sufficient to have your lip motion that looks more like natural. Yes?
It seems to me like the system is not really all that specific to Korean. Other languages with symbol vowel inventories, even English,
Right.
you might expect it to have reasonable performance on even without further tuning. Is that the case, or is that just an incorrect interpretation?
Right. I mean, it is not language dependent because we're looking at only acoustics.
Yeah, maybe we can try something. In the text input that you have,
Right.
if you are writing, let's say, a word like
Or can you transliterate?
the Coca-Cola Company, how would you write this in Korean with the nearest part?
Can you transliterate English into
So
Korean?
once again, if that's going to drive the list, but there's no speech recognition in between.
Right. No, that's all right.
All right. Okay, I'll do that. All right.
And let's see how it goes.
안녕하세요. 만나서 반갑습니다.
Sorry. What was that?
Coca-Cola.
Coca-Cola?
Coca-Cola Company.
Do you speak some Korean? You know how to say Coke.
Okay. This is the Coca-Cola Company. As trying to closely match.
Okay.
All
Alright?
No, there's no speech
so you
recognition.
have to kind of be in sync, okay?
Yeah, okay.
The plosives. That's
What do you
Yeah.
think?
it's missing the.
Yeah, the
The
consonants.
bilinguals.
All right, let me just run that over again. The Coca-Cola Company.
The N isn't too bad.
The L was bad.
The L was bad. That was the problem. Yeah.
It was like
There's
Coca,
one that was a little bit missing.
Coca-Cola Company. So the
Well,
efficiency-
Coca-Cola. Yeah, it's
So the
really
efficiency-
Did it? Okay. Oh, I didn't think there was lip closure there.
Yeah, I mean, I think, I don't know about Korean phonology, but I think in English, like, plosives are it's like a very, very big clue in terms of recognition. It's like the buds. It's a very, very expressive.
Well, there's a lot of place of articulation that you're able to read on. So you can,
But also the lip movement. So it's very
yeah.
distinct. It's
Well,
not
there's also lip movement around the vowels and so forth. It's not just on mouth aperture. Right.
Right, it's less consonant vowel, it's more blends too.
So
Anyways, it might get looked
There's
more
diphthongs in
realistic.
English too.
Oh, they're not.
English
anyway,
has
so
more
I'm
diphthongs
looking
than like any
for
other.
your suggestions as to improving detection, segmentation, and recognition. Okay? Okay, so I'll be here for the next until next summer. So I'm always, my door is always open.